So now what we're going to do is we're going to take a sequence where it has a limit inferior. So the limit inferior as n approaches infinity of an exists, and we're now going to call that value L. And what we're going to do is we're going to prove that this sequence has a subsequence that converges to this value L, i.e. that the limit inferior is a limit point for the sequence, and we're going to show that it's the minimum of the limit points, i.e. that there cannot be a subsequence of your original sequence that converges to some value that is strictly less, than the limit inferior. And this is going to be quicker because basically it's the exact same arguments as we've used for limit superior, but in the other direction. So let's begin with finding a subsequence that converges to the limit inferior. So the strategy is going to be the same. We're going to take progressively smaller intervals, and for the first term of our subsequence we'll start with an interval of radius 1, so the interval L minus 1 to L plus 1. So we now go to the fact that the limit inferior exists, and that means that the sequence of infimums exists and converges to this value L. And I've written out a little bit of that sequence here, so it's I1, I2, I3, and it is converging to this value L. And remember, it is a monotonically increasing sequence, so it comes up and converges to the value L. So by the definition of this converging, I can find you a term in this sequence, which I'll call IN1, such that it and all the terms beyond it are within this interval of radius 1 around L. Then what I do to find a term of the sequence that is actually inside this interval of radius 1 around L, I remember the definition of this IN1. It is the infimum of all elements or all terms of the sequence from AN1 onwards. So it's the infimum of this set. Now, it being the infimum means that it is the greatest lower bound. So it is a lower bound for all of these things. It's less than or equal to them, but also it's the greatest. So anything bigger than it is not a lower bound in particular. And note also that I've put IN1 on this side of L. I know that it's not on this side of L. So it's at the maximum, the biggest possible value it could be is L itself, but it's more likely to be one of these values less than L. But I categorically know that it's not in this half of the interval that's bigger than it. So now what I can do is I can look at IN1 plus 1, and I know that that value is going to be, well, here on the picture, but the maximum it could possibly be is up at L plus 1, and that would be the case where IN1 was equal to L itself, but it's more likely to be less than that and not on that border and inside here. So now what I can say is this value IN1 plus 1 is not a lower bound for this set, because if it were, it would contradict this being the greatest lower bound for that set, and therefore since it's not a lower bound, it must be the case that there is something in it that is strictly less than it. So I can therefore find that thing that is inside here that is strictly less than this, which I also know will be greater than or equal to this, because this is a lower bound for the set, and therefore it's going to be strictly less than this, greater than or equal to this, and therefore it will be inside this interval of radius L around, of radius 1 around L. So I will use that term that I found that is inside this interval as the first term of my subsequence, so I'll call that AM1. Now, to find the second term of my subsequence, I will then look at the interval of radius 1/2 around L, which I've started to draw here. So here's L minus 1/2, here's L plus 1/2. And again, what I'm going to do is, by the fact that I know the sequence of infimums converges up to the value L, I'm going to find this infimum N2 such that it is inside this interval of radius 1/2 around L. But I'm also going to select N2 more carefully. I'm not just going to make sure it's inside this interval, but I'm also going to make sure that it is strictly greater than M1, this term that I've used as my first term in my subsequence. And again, that's to make sure that this thing that I'm going to put in as the second term is strictly beyond this one in the original sequence, to make sure that what I'm constructing is actually a valid subsequence. And then it's the same argument. I look at IN2 plus 1/2 now, not plus 1 plus 1/2. You need to update this number according to which interval size, which interval radius you're actually at the moment. And I know that this cannot be a lower bound for the set that this is the greatest lower bound of, because if it were, it would contradict that being the greatest lower bound, and therefore I can find something from the set that this is the infimum of that is strictly less than that, but greater than or equal to that, and therefore is inside this interval of radius a half. And I'll take that as then my second term in the subsequence. And then you continue on. You go to the interval of radius a third for the third term, the interval of radius a quarter for the fourth term, and the interval of a radius a fifth for the fifth term, and so on. For the kth term, you'll be looking at the interval of radius 1 over k. So in that way I will construct this subsequence of the original sequence, and hopefully again you appreciate that this is going to converge to L because of the way that I've constructed it so that each of these terms is in a progressively smaller and smaller interval. Therefore, the terms of this subsequence are getting and staying indefinitely close to this value L, so this sequence is going to meet the criteria for converging to the value L. So I've hence proven that if you have a sequence where the limit inferior exists, then there is a subsequence always of the original sequence that converges to that value of the limit inferior. Hence the limit inferior is a limit point of the sequence. So now what I want to prove is that it is the minimum of the limit points for the sequence, and again we're going to do that by contradiction. So suppose, for the sake of contradiction, that in this sequence where I have a limit inferior, that there is a subsequence that converges to a value L tilde such that that value L tilde is now strictly less than the value of the limit inferior L. So on my picture, here's the real line, here is L, here is L tilde. Once again, what I'm going to do is take that distance between the two, which now, because L is greater than L tilde, is L minus L tilde, whereas on the other side, when we were doing limit superior, it was L tilde minus L, because we were supposing L tilde was the bigger one. So L minus L tilde is that distance between the two, and then take a half of that, make that your epsilon, and then I've drawn these epsilon intervals around my L and L tilde. Here is the epsilon interval around L, here is the epsilon interval around L tilde. So again, because the sequence of infimums converges up to this value L, I know that if I use this epsilon in the definition of convergence, I can find you some infimum I big N such that it is inside that epsilon interval around L. So I've got this one here. I also know by the fact that this is converging to L tilde that again I can use this epsilon in the definition for this one converging, and I can find you a term in that subsequence which I'll call AN big K, such that it and all the terms beyond it are inside that epsilon interval around L tilde. And here is the problem, that everything that is inside this epsilon interval around L tilde is going to be strictly less than this value I big N here, which is inside this epsilon interval around L. So I can therefore conclude that all the things in the tail end of this sequence are strictly less than this value IN. But here's the problem, IN by definition is the infimum of all things in the sequence from the big nth term onwards, so AN, AN plus 1, etc. So that means that it is less than or equal to everything that is inside this set. But of course, eventually, we're going to get to a point in this tail end of this subsequence where all of the things are now in this portion of the sequence in this set. And hence we have a contradiction, because those things are all going to be less than this, but they also have to be greater than or equal to it. So therefore it cannot be the case that this subsequence converging to this value L tilde that was strictly less than the value L existed. Ergo, that is the smallest of the limit points of your sequence when the limit inferior exists. So I'm going to stop there. Thank you for watching, and I hope you found that useful.